full representation of an equation. Remember the general form. Pen is glitching. Is f of x equal to ax squared plus bx plus c. The vertex form is f of x is equal to a times x minus h squared plus k. All right. The a value, just as it is for the general form, is the 1 unit slope. The h and k values represent the vertex. H comma k is equal to the vertex. So if you have an equation given in the vertex form, sometimes called standard form, so I'll write AKA standard form, you would know some pretty useful information, right? Most notably the vertex. So in the examples that follow, and we'll have to talk about in a couple minutes how we get an equation from general form to the vertex form, but we'll get there in a sec. Right? But if you're given an equation that's already in the vertex form, you can pull the vertex directly from that equation. And if you know the vertex, you know the axis of symmetry. Right? So a lot of good stuff there. Right? So looking at that first example here, all I would really be doing is matching that up to the standard form, or the vertex form. So f of x is equal to a times x minus h squared plus k. Well, the k will be 3 in a sec. Right? So we have certain pieces to this equation that need to be equal to one another. There's shortcuts, but let me show you the long cut first. All right? So it's not really that long. It's just a little longer. All right? So we have the understood coefficient of 1 in front of the x minus 5 binomial. All right? What we're going to do is set all the relevant parts equal to one another. So we're going to set the a value equal to whatever the number is in front of the binomial squared. We're going to take the content of the binomials and set those equal. And we're going to set the k value equal to whatever that loose constant is. All right, so we have 3 equations that we get from this. A equals 1. X minus h is equal to x minus 5. Positive k is equal to positive 3. All right. Some of this has a little bit of unnecessary fluff. Like, for example, positive k equals positive 3. You can go ahead and just write that as k equals 3. It's the middle equation that we have to solve, because I have my a value. I have the k value. I just need the h value. All right. So if I solve this equation, I would do it by subtracting x from both sides. Fortunately, it cancels. So we're left with negative h is equal to negative 5. Then if I divide both sides by negative 1, I get h is equal to 5. All right. So that tells me that my vertex, which is always h comma k, is going to be equal to 5 comma 3. All right, so that's a very procedural way of doing it. It's a little lengthier. There are some shortcuts, right? Well, the most notable shortcut is you take the opposite sign of whatever is contained within the parentheses, whatever number, make that your h value, and keep the sign of whatever is outside the parentheses as the add-on at the end and that would be your k value. Right? The issue with that approach is that if there's a coefficient in front of the x inside the parentheses, it wouldn't be in vertex form, and that's like kind of the basis of a trick question. Right? So you just got to be careful about little things like that. But I could look at number 4 directly and say my vertex is going to be 5, 3.5. Right? Take the opposite side of the thing in the parentheses, keep the sign of the thing outside the parentheses as the add-on, and that would be your vertex. But again, procedurally, we have the 3 components, and I have my standard form, or my vertex form. So if I wanted to show the work, or maybe I needed to show the work, I could then say a is equal to 2, x minus 5 is equal to x minus h, and 3.5 is equal to k, or I could just say k is equal to 3.5. Right. So then again, it's just a matter of solving that middle equation. The x's would cancel. If I subtract x from both sides, it's going to wipe out. You get negative 5 is equal to negative h, making h equal to 5. All right, so my vertex again would be 5, 3.5. But if you look at number 2, for example, that doesn't look like it's in the same form. Basically, it's a fairly straightforward process. The only way that they can make this difficult is to try to trick you with the form of the equation that they give you. All right? So if I look at number 2, I'd say, well, that doesn't look like it's in vertex form. But I can write it as y equals x minus 0 squared minus 2.5. And I'll even put the understood coefficient in front. This is an equivalent equation. Right? If I simplify it, it ends up being exactly the same as what we started with. So then I could use my process, or I could just use the shortcut. We don't have to worry about taking the opposite sign of 0, because 0 with a positive or negative in front of it is still 0. So my vertex here would be 0, negative 2.5. Right? But again, like I said, you could show the work, you can match it up by getting your 3 parts. And so you'd say a equals 1, x minus h is equal to x minus 0, and k is equal to negative 2.5. And then when you solve, you get h is equal to 0, making your vertex, again, 0, negative 2.5. Right. Number 3, again, same deal. It looks like it's probably not in vertex form, but if I make a couple of little adjustments, it would make it vertex form. Right? So it needs to have this structure. Right? So it needs to look just like this. It doesn't yet, but we can make a quick modification, and it will. All right? So put a 1 in front and a plus 0 off at the end, and now you have it in vertex form. All right? Very slight adjustment. So then I could use my approach, or I could use the shortcut, and I can get all the necessary information out of it. All right, so the a would be equal to 1, x minus h would be equal to x plus 4, and k would be equal to 0. Since we know that x's are going to cancel out every time, we could just wipe that out immediately. We're saying negative h is equal to 4, making h equal to negative 4. All right, so it's just reinforcing the idea that whatever the sign is of the term, the numerical term in the parentheses, we flip it, we reverse it. And that becomes the sign of the x value of my vertex. Whatever the sign is of the k value, we keep that. So -4, 0. All right? And again, this method, you'd only have to use it if the question said to show your work. If it didn't, probably just throw it right in the calculator and take a look. You know, go into the table of values. All right? So, you know, it kind of makes itself only necessary if the directions make it necessary. All right? But it's nice, once you get the hang of it, you say, oh, the vertex for number 5, my vertex is -1, 8. Sorry, -1, -8. Because I'm flipping the sign of the numerical term in the parentheses, and I'm keeping the sign of that trailing term, whatever it is, positive, negative, that comes along for the ride. You could also be asked to write an equation. 33. So you could be asked to write the equation given some information. What they're telling us here is the h and k value. They're not telling us the a value. They're saying write a quadratic equation. They're not saying write the quadratic equation, because there are infinitely many possibilities. Right? They could all have the same vertex, but with different a values. So you get to select the a value here, but then the h and k are given to you. So I have, again, my model. I know the h value has to be 1.9. The k value has to be -4. All right, so I'm just popping those values in. And the a value, I can make whatever I want. All right, so I'll go with the simplest case. I'll go with a 1.
Wouldn't the h value be -1.9 since we flip it?
So in this case, because it's given as a coordinate, you keep the sign. It's only when you're extracting it from the equation that you flip the sign.
Oh, okay.
It's actually going to get flipped in a second once I put it into the equation. So we're going backwards here. We're starting with this, and we're going here, but we haven't done the part where we actually make the substitution yet. All right, so that's going to happen right now. So we're going to say f of x is equal to, pick an a value, I'll go with 1, keep it simple, x minus whatever the h value is, squared, plus whatever the k value is. All right, when I put the h value of 1.9 in, now it went from being positive as an h value to negative as part of the binomial. Then I'm directly substituting the -4. I can clean it up a little bit. Sorry. And get this equation. All right. Now, just for a quick demonstration, I'm going to go to Desmos, but it's not, for the purpose of, doing the work. I just want to show you something that I think is kind of cool. Cannot type. Desmos.com. So we have this equation, f of x is equal to, we used 1, but I'm going to leave it as an a value, x minus 1.9, close it up, square it, minus 4, and I'll create a slider for a. So you'll notice here that my vertex is 1.9 comma 4. All right? I'll even pop that in. Bless you. Sorry, -4. All right? No matter what I make my a value, it's going to be pinned to that vertex of 1.9 comma negative 4. All right, so it'll get skinnier, it'll get wider, it'll even flip over, but the one thing that'll remain constant is that vertex, 1.9 comma negative 4. All right, so it really truly does not matter what the A value is. If you want to have an equation whose vertex is whatever, you can leave the A variable and only substitute in the other information. All right. So, pretty cool. Now, in the next set of problems, they're going to ask us to choose a particular A value that's other than 1. Well, it's the same approach. All right. So, if you look at that, like for example, number 9, write an equation whose graph will have the vertex, and so don't use a leading coefficient of 1. That's fine. So use a leading coefficient of 2, or 10, or 30, or negative 5. It doesn't matter. All right? But it's really the same type of problem. So my H value is 100. My K value is 200. And I'm popping it into the function. I'll let A equal 2. So x minus the 100, see, that's where we get the sign change by substituting it into the equation. So when I take an H value and substitute it into the equation, or extract the H value from the equation, that's when the sign change occurs. All right. Plus 200. And that's really only because the formula has the minus sign already built into it. All right? That's where you get the sign change, because I'm saying x minus whatever the H value is. If the H value is negative, it's x minus a negative, making it positive. If the H value is positive, it's x minus a positive, maintaining it as a minus sign.
For number 7, since there's a 0, does it matter if we do x plus 0 or x minus?
It wouldn't make a difference, because it's just going to become an x anyway. All right. So looking at number 11 real quick, all the other problems are just kind of redundant. All right. But it's saying describe the similarities and differences between the two equations. Well, the first thing that I would do for something like this is write it in the vertex form, each one. I'll just throw that there. Stop moving. So we're going to have y equals 1 times x minus 0 squared plus 1. And the other one would be y equals negative 2 times x minus 0 squared plus 1. All right, so they're both in the vertex form. And you can see the h and k values are going to be the same. All right, so they will have the same vertex. All right. The first one is going to open upward because it's got a positive a value. All right. So its 1 unit slope is equal to 1. All right. So it opens up. The second one opens down. The other thing that we could talk about is the width. All right. Bless you. So if I have an a value of 1, you look at the width of the parabola, this is your standard parabola, versus a negative 2, the parabola it's skinnier. All right. If I make that a value really large but in the negative direction, it gets really skinny. I can do the same thing in the positive direction. The larger the number, the skinnier the parabola. All right. So this one is going to be wider, and this is going to be narrower. But they will have the same vertex. All right. Because the only thing that differs between the two of them would be the a value. and the A value just talks about the width based off of the 1 unit slope.
So it's not,
And
it's
direction.
not asking if it's positive or negative, it's just asking which one has a bigger slope.
Yeah, basically, yeah. All right, but then, you know, you get to this concept, it's like there's so many different approaches that could be made or taken to figure these things out or make use of this information. But then you always come back to the idea, what if the equation you're given is not in the vertex form? What do you do? There's a couple of approaches that could be used to put an equation in vertex form. One is the completing the square approach. All right. So number 12, for example, well, we want to apply completing the square, but I can tell you that what we're going to do here is going to be simpler than the completing the square approach that we use to solve quadratics, right? Because basically all the hard stuff is going to be removed, all right? But we start off the same way. We get rid of the C value, whatever it is. Bring it over to the other side and leave a blank, right? So I'm going to write this as x squared plus 4x, and I'm going to leave a little blank to complete the square. And on the other side, I'm going to write y minus 12. All right. When we use completing the square to solve, it was always equal to 0. So the right-hand side didn't contain a y. We didn't have a second variable. Now we do. All right. But we do have to do our side work. All right. So take our b value, cut it in half, then square it. All right. So my b value here is a positive 4. So 4 over 2 squared. 4 divided by 2 is 2. Squared is 4. That's the number that gets chucked into the gap. It will be a perfect square trinomial. All right, so remember the approach that we used there. Take the square root of the first term, the square root of the last term, carry down the sign of the middle term. All right, so square root of the first term goes here, square root of the last term goes here, carry down the sign of the middle term. So x plus 2. On the right-hand side, we have a y minus 8. All right. Now, if this were completing the square to solve a quadratic, we'd have to take the square root of both sides. It would get messy. We'd have the plus and minus. None of that here. All I have to do now is add the 8 back. So I'm going to get y is equal to x plus 2 squared plus 8. And now our equation is in standard form, or vertex form. All right, so we did our little side work, wasn't too crazy. We used that to help us complete the square, but then once we did that, we factored, and then that was the end of it. All right. Now, for number 13, we have a leading coefficient that's not equal to 1, so we have to make that adjustment.
I'm sorry, why did you add 4 to negative 12?
Oh, because when you do the b value cut in half and squared, you always add it to both sides of the equation.
Thank you.
No problem. All right. So we have to correct for that leading coefficient, that negative 1. So we'll do that by dividing each term by negative 1. Thanks, dude. So basically dividing both sides of the equation, or multiplying, because it's just a negative 1, it doesn't make a difference. All right, so divide by negative 1, divide by negative 1. So we're looking at this really as negative y is equal to x squared plus 12x plus 7. All right, I'm going to vacate the c value, so I'm going to get rid of that. Yeah?
What would it be minus 7?
Thank you. Good catch. So I'm going to add the 7 to both sides to get rid of it. X squared plus 12x, leave a blank to complete the square, is equal to negative y plus 7. We're going to do our side work. So I'm going to take my 12. I'm going to cut that in half and square the result. It's going to give me a 36. So I'm adding 36 to both sides. All right. Factor the trinomial on the left. So x plus 6 squared. Because remember, again, square root of the first term, square root of the last term, carry down the sign of the middle term. Then I have negative y plus 43. Then the only thing that remains here is to solve for y, get y alone. All right, so basically undoing the first couple of steps. So I'm going to subtract the 43 from both sides. X plus 6 squared minus 43 is equal to negative y. And then I'll divide each term by a negative 1. Right? Remember, there's an understood coefficient in front of the binomial squared of 1. That's what's going to get divided. So when I divide each term by negative 1, I'm taking the 1, let's get a fresh new color here. The 1 and the negative 43 are the only things getting divided. Right? We don't have to divide the contents of the binomial squared because that would get accounted for if I ever distributed it out. Right? Just by dividing the 1 by the negative 1, that would allow for that to work itself through the expanded binomial. All right. So we're looking at negative 1 x plus 6 squared plus 43, that's equal to y. All right. They only asked us to get it into vertex form, but we actually could pull out the axis of symmetry and vertex from this. All right, so just by getting it into this form, we have something that's pretty user friendly. All right.
Could we just put for the last one? We could just put negative because negative 1 and negative.
Yeah. All right, so the next couple of problems are just kind of like, I guess, beating this to death. So I'll leave this up on the big board, but I'd like you to do the next page for homework to be submitted. All right, so it's really the 3 concepts we worked on. Pulling the vertex from the equation, writing an equation given the vertex, and then writing it in vertex form with completing the square. Like I said, let me leave this up on the big board.